Many of the air handler and chiller plant inputs in the CBOA tool are representations of system performance trends. The tool prompts users for regressions of system performance. For example, the AHU heating and cooling worksheet, shown here, prompts users for a regression of cooling plant efficiency. This tutorial will discuss how to develop regressions and how they can be entered into the CBOA tool. First, let's discuss how to create a regression for air handler, supply fan, airflow, and we'll show what that looks like over on the air handler worksheet. As shown here, the CBOA tool needs 4 points for the supply airflow regression. These right here. And it assumes a linear relationship between each point. So let's go to a separate file from the CBOA tool. This is not a worksheet included in the CBOA tool. This file shows trend data from an air handler for a project. For this project, we don't have specific data on the supply fan airflow, but we do have data on the supply fan speed, shown in this column, which is a typical situation. We'll assume that supply fan airflow varies linearly with supply fan speed, and that at 100% speed, the fan delivers 100% of design airflow. One way to help validate these assumptions would be to measure the air velocity at the filters in the air handler and convert this to CFM. Then compare this to the fan speed at the time of the velocity reading. If we plot this fan speed data versus outside air temperature in this column for times when the fan is on, we get the blue points shown on this chart. This chart is showing supply fan speed on the y-axis versus outside air temperature on the x-axis. And the black line on this chart is a curve fit of the trend data. The r-squared value of this curve fit is 0.55, which is an indication of a reasonably good fit. It trends in the direction we would expect, namely increased fan speeds at increased outside air temperatures. So choosing points from this curve fit, we would choose at 50 degree outside air, 62% speed. At 55 degree outside air, we have 68% speed. 60 degree outside air, we have 74%. And at 65 degrees, we have 80% speed. We can enter these into the CBOA tool. So let's go ahead and do this for that regression. First, we'll enter in our points for outside air temperature. We have at 50, 55, 60, and 65. Then our airflow percentages, which are 62, and then 68, 74, and 80%. And the other inputs that are on this worksheet are covered in another tutorial lesson. And note that the curve on the right-hand side updates as we enter in those values. For outside air temperatures outside of the regression, namely above 65 degrees and below 50 degrees, the CBOA tool assumes the performance of the last point. So at outside air temperatures below 50 degrees, the CBOA tool assumes the fan is delivering 62% airflow. And at outside air temperatures above 65, the tool would assume the fan is delivering 80% airflow. And it's up to the user to estimate how the system will perform outside of the trended values. You could assume that supply fan airflow would continue to rise above the trended outside air temperatures, but for this instance, we've assumed that it will stay at 80%, since we don't have data that suggests otherwise, and maybe the building operator indicated that they never see the fan operate at 100% speed. A screenshot of this chart, let's go back to our air handler file, a screenshot of this chart can be included on the documentation worksheets of the CBOA tool. For instance, right here, we've just pasted this in by taking the doc template worksheet and copying it and renaming it as AHU supply fan airflow. The trend data can also be included in the documentation worksheet if desired. When gathering trend data for developing regressions, try to gather data that covers most of the operating conditions of the related system. This will increase the accuracy of the regressions. For the airflow example that we just presented, trend data was gathered during outside air temperatures from 49 degrees up to about 66 degrees. which is only 30% of the outside air temperature range of 35 degrees to 95 seen by the building during operating hours. However, these outside air temperatures represent about half of the bin hours. Gathering additional trend data to cover a greater range of the bin hours would likely increase the accuracy of the regression that we developed. Now let's look at another example of how to develop a cooling plant efficiency regression for entry on this worksheet here. Here's a separate file from the CBOA tool. This is not a worksheet included in the CBOA tool. This worksheet shows chilled water plant trend data that was gathered from a building automation system. Here we have the points of the date and time, outside air temperature, chilled water supply temperature, chilled water return temperature, the power draw of the chiller, and then the power draw of the pumps and the cooling tower fan, and the chilled water flow rate in GPM. In this example, 2 weeks worth of trend data was gathered. We'll show how this trend data, along with chiller performance data from the manufacturer, can be used to develop regression-related inputs required by the CBOA tool. Note that this type of trend data may not be available for all projects. It's up to the tool user to utilize the data available for a particular project to develop the input regressions. We can use the trend data to calculate the chiller cooling load based on chilled water flow rate and chilled water supply and return temperatures right here and in tons. The efficiency of the chiller and the chilled water plant in units of kW per ton can then be calculated. Note that there is a difference between the two. We can then plot this data against outside air temperature to get the relationships shown here. For both chilled water plant efficiency, shown on this chart, if I scroll down, and chilled water cooling load. We could enter average points from the chart shown here into the CBOA tool as inputs for the regression. And let's go back to that regression to remind ourselves what we're looking for. Outside air temperature versus plant kW per ton. But what we don't know is how the efficiency varies at outside air temperatures outside of the trended range. You can see the range of outside air temperatures used by the CBOA tool for a particular climate zone and equipment operating schedule on the demand worksheet. So let's go to the demand worksheet of the CBOA tool. We'll zoom in here. Here we see that the outside air temperatures for this example project range from 35 degrees, it's a low in January, to a high of 95 degrees in the month of September. However, the trend data is only for outside air temperatures between 48 degrees and 66 degrees. To help determine the best fit across all outside air temperatures, we can compare this trended data to manufacturer's data. The yellow highlighted data shown on this worksheet is from the chiller manufacturer. Using the chilled water load versus outside air temperature regression from the previous worksheet, so let's take a look here. This equation right here, this regression for chiller tons versus outside air temperature. We can translate the tons value from the chiller manufacturer to outside air temperature. And here's that equation you can see in the cell up there in the formula bar. Now we can chart this data. Let's go ahead and do that. This chart is showing outside air temperature on the x-axis and the efficiency of the chiller on the y-axis. The red points on this chart represent the data, and the red line is a curve fit of this data. Note that the performance is non-linear. The efficiency drops at lower loads, meaning lower outside air temperatures. If we superimpose the chiller efficiency trend data on top of this curve, so this is the trend data, which is the brownish orange points, we can see that it matches closely. This means that it seems reasonable to use the chiller manufacturer's trend data for developing the regression. Going back to the data worksheet, we can then add the power draw of the pumps and the cooling tower fan to the chiller power draw to obtain a regression of cooling plant efficiency versus outside air temperature. These points are highlighted green here in this chart. Note that the plant efficiency is different from the chiller efficiency due to the pumps and the cooling tower fan. The green points in line are our regression of chiller plant efficiency versus outside air temperature. We can now select 4 points to use in the regression for input into the CBOA tool. We want to divide the data up into 3 linear segments. In looking at the data here, it seems that the 4 points that would give the best representation of 3 linear segments are at 38 degrees, at around 45 degrees, 60 degrees, and then 95 degrees. At these points, the cooling plant efficiency is 1.24, 0.92, 0.67, and then 0.6 kW per ton. So let's go ahead and enter these values into the CBOA tool on the AHU heating and cooling tab. So first we enter our outside air temperatures of 38, 45, 60, and 95. And then our kW ton values from that previous chart we enter in right here. And that's an example of how to develop a cooling plant efficiency regression for input into the CBOA tool.